Hi there, my name is David Stewart. I'm a researcher in the Materials Science Department here at the University of Maryland, and this video is about a superconductor on a magnetic track. With this time, the track can be rotated upwards to 180 degrees. So this is our Type 2 superconductor. It's a little bit pre-chilled at the moment. It's very cold. And this is a cup full of liquid nitrogen that will cool it down, back down to full 77 Kelvin. We'll do that in the presence of this magnetic field. The magnetic field on the track is oriented so that the field lines travel from this outer region to the center region. So this is north-oriented, this is south-oriented, back to north. So we have two loops of magnetic fields that travel in these directions. And what that's going to do while the superconductor is cooling down, it's going to enter its superconducting state and begin setting up electric currents, which will exist to counteract the magnetic field of the permanent magnets. And because it's a superconducting current, it's going to be traveling with zero resistance, and that means that there's basically nothing to stop it from moving once it's removed from the liquid nitrogen. And that's going to end up pinning the superconducting puck in place above the magnetic field. And you can feel that pinning effect as you try to bring it closer, kind of locks in position. Now, even though it's locked at a certain height, it is free to travel back and forth on this track. Well, one good question comes up. If I give it a rotation, what will happen to it? Will it stay hovering at its exact height? Will it change to a different height, or will it simply fall off the track entirely? Okay, so it's cooled down to liquid nitrogen temperatures. I can rotate it 90 degrees, and we see that it remains locked in place. And the reason that it remains locked in place, even though there's now the force of gravity trying to pull it off the track, is that in order for the superconductor to move away from the fields, all of the currents that are set up inside of it would have to be modified. And you can do that with your hand by pulling it off. You can apply enough force to do that for sure, but gravity itself is simply not strong enough to modify every electric current in this superconductor. Now, the currents themselves are set up kind of in many loops around all the magnetic field lines, and they actually create what's called a magnetic vortice. Each of those currents has a counteracting magnetic field that interacts with the external permanent magnetic field and provides this locking mechanism. So in order for that mechanism to be unlocked, you have to apply enough force to destroy those vortices throughout the entire superconductor. Okay, I said this track can go 180 degrees. So what happens when we turn it all the way upside down? Will the puck still stay in exactly the position, or now that the force of gravity is going with the magnetic field lines, will it be repelled off, or will it actually get sucked into the magnets now that all the forces have varied? So that same explanation of the pinning effect and the forces required to undo that pinning explains why, even at 180 degrees, the puck stays on the track. There's no more, gravity is not acting any stronger at 180 than it was at 90. So these forces are still not enough to undo the magnetic pinning.